start with problem 1. Okay, so we're supposed to check that the affine Grassmannian classifies these pairs of principal bundle and some isomorphisms. So to do this, let's introduce one more trivialization, and then we'll see what happens when you do this. So let's consider the following space. Okay, a space of triples such that P is a G bundle on X. Phi is just as in the problem, so phi is a trivialization of P restricted to X minus the little point X. And phi is a trivialization on the formal neighborhood of X. So P dx. Okay. Now let's try to understand what this, the information that this contains. So this thing just tells us that this P bundle is trivial on X minus X and on this formal neighborhood. So the only information that this thing actually contains is the transition function that these two open sets give us in the intersection. So let me define a map from this to GK as follows. So if I have a triple like this, I define an element of GK by doing the following. So I start with the trivial bundle on dx star. So the open formal neighborhood around X, the punctured disk. Now using phi, this one here, I can get trivialization of the G bundle that I was given, right? And using the inverse of this map, I get a map to the other trivialization. So this gives us an endomorphism of the trivial bundle in element of GK, because K is the algebra function of the puncture open disk. And similarly, if you're given an element G here, G, I can construct this set of data by, well, I'm going to write it in words, but just use G to glue this trivial bundle at X minus X and trivial bundle at dx along dx star. Okay, so great. We have identified something else, but that was not the point of the problem. So what to do now? Yeah, and these maps are obviously inverse to each other. I'm not going to check, but you can check. Okay, and now what do we do with this space of triples? Well, we have a function from this space of triples to just the space of pairs, as in the problem, just by forgetting the third thing. And we saw this is isomorphic to GK. So we want to try to understand in terms of this what it means to forget this trivialization. So first of all, let's try to understand what the fiber of a map here is. So, of a point here is. So, to begin with, if we take any G bundle and restrict to this formal neighborhood, it's going to be trivial, because every G bundle on the disk is trivial. So I can choose a trivialization. That means this map here is surjective. Oops. OK. And given one trivialization, any other trivialization just differs by an endomorphisms of the trivial bundle on dx, which is just an element of GO. So basically, this thing here is a GO bundle. And again, I'm not going to check, but I think that's the correct order of the map, but maybe it's the inverse of that, whatever. But with one of the orders, you get that this GO bundle is, in fact, the quotient of GK by GO on this side, and we get the identification that we wanted. Any questions? OK. So let's move on to B. OK, so in B, a trivial bundle here if it was trivial, that means that I can choose up here some trivialization here and some trivialization here, such that the transition map is also trivial. I mean, that's what it means to be trivial. Right. So basically, the trivial bundles here, up to changing the trivialization here, give you the identity here. But what does it mean to change these two trivializations? Well, we already saw changing this trivialization is multiplying by GO, and changing the other trivialization is multiplying by some automorphism of this trivial bundle on the on this open part of the curve. But endomorphisms of this of this trivial bundle on x minus x is given exactly by G of C of T inverse, which is O of x minus x. So in other words, the let me say the trivial bundle can be given by two trivializations plus the identity map. So by changing trivializations, we get that all the elements on the top are given by GT inverse, which are automorphisms of this, times GO. And so the image here is this thing mod GO, which can be checked to be isomorphic to GT inverse mod G. And further, there's a question about openness. Oops. So yeah, it asks to check that this subspace here is open. And to do this, this space here is homogeneous. So if it's right, like we can just compute the tangent space by computing it in one point, and everywhere else it's the same. And to compute the tangent space at the identity of this, well, it's very easy. It's just given by GT inverse over G equals the tangent space of And similarly, if we want to compute the tangent space of the Grassmannian at the identity, the affine Grassmannian at the identity, it's just given by G of K mod GO with, and the inclusion gives here an obvious map, which further is obviously an isomorphism. Oops. Okay, and okay, this is a true statement in finite varieties, and you can make it true for int schemes also, because you can reduce to finite things. But if you have some two smooth spaces, and well, one smooth space and one smooth subspace, and their Lie algebras coincide, then that space was open. So yeah, this implies Ger0 open. Okay. And now for C, I'm not going to prove the result. I'm just going to invent the answer and let you check the result. But it's pretty similar to what's going on in A. So the set of things that this classifies should be G bundle, a trivialization, just like above. And E is a reduction to B structure. So that means so yeah, P G bundle, phi a trivialization, and E is a reduction to P structure of P reduced to the point. So that is a map from B to P restricted to X, to little x, that is. Well, yeah. And yeah, you can check that this thing here is going to correspond in the same way as there to the affine flag variety. Okay. Any questions on problem 1? Oh, perfect. Okay. I'm going to skip problem 2 because we don't have too much time. And I'm going to do problem 3. Okay. So, right. We're supposed to look at T lambda, which for SL2 looks something like, with lambda dominant, which for SL2 looks something like this, for some positive integer n. And we're supposed to check that the stabilizer of this point acts non-trivially on L0. So let's first compute the stabilizer of this point. So this is just T lambda GO T minus lambda intersect GO. And if you do this computation, you can check that this is O T to the 2n. Yeah, something like this. Is this correct? Maybe it's the other way around. Something like this. Okay, so then we need to try to understand how this acts on the fiber of L0. And even though we haven't done it, we have a description of the fiber of L0 in problem 2. So let's try to see what this point corresponds as a lattice. So T lambda as a lattice corresponds to the lattice generated by Tn E1 and T minus n E2. And so this is L. So if we consider L mod L0 intersect L, this thing is given by T minus n E2 over E2. And L0 mod L intersect L0 is given by E1 mod Tn E1. Okay, actually it's this star. Right, in fact, because this is SL2, they're sort of the form like A plus TO, A inverse plus TO, and then O and T to the 2 and O. So once we take the determinant here, how is this going to act? Well, it's going to act on this thing basically just by A inverse. And because this is n-dimensional, when I take the determinant, it's actually going to act by A to the minus n. So, right. Let me give this name this group a name, H. So H acts on determinant of L over L0 intersect L as A to the minus n. And similarly, it acts on determinant of L0 over L0 intersect L through this factor here, so it acts as A to the n. And so when we take the product of the dual of this times this one, it acts in total. Oops. Well, let me write it here. So H acts on L0 by A to the 2n, which is in particular non-trivial unless n is 0, which is what we need to check. Okay. Okay. And now we need to use this somehow to check that there's no, well, yeah, that basically there's no D modules with monodromy Q away from this identity point. So what does this actually tell us? So if we consider, the torus inside this stabilizer group H, this torus is GM. Then the equivariance tells us that, well, it tells us much more than this, but it tells us in particular that if I have the action map from T to T dot, well, okay. I want to say T dot T lambda, but I mean, like, how should I write this? Oh, let me say L0. Right. This acts on this L0. So by this, I just mean an action map on a point. So just pick one point, and this is the multiplication map by that point. So it tells us, if we call this A, it tells us in particular that the A pullback of a sheaf M is trivial. Trivial. Okay. So, but if we look at this map, this is just the map from GM to GM given by multiplying by 2 to the n. T goes to T to the 2n. But further, we know that this M has monodromy Q. So if we sort of go around this GM once, it gets multiplied by Q. So if it goes around this, the GM 2n times, it gets multiplied by 2n. So let me write this. So m as German q. So if you go around gm, it gets multiplied. Right. So, so going around this GM 2n times corresponds to going around this GM once. So that means that this pullback of m, when I go around GM once here, I get multiplied by q to the 2n. So star m. But it's trivial, so unless q to the 2n is 1, this can't happen. So in particular, if q is not a root of unity, this can never happen. And so there's no sheaf with q monodromy away from the point. And it's easy to check, but I'm going to omit the details, that on the point, you can only be trivial. So that's how you're equivalent to the category of vector spaces. OK. Any questions? Yes? Yeah. So equivariance says, right, like, well, equivariance says that you know, like h acts on L0, we've seen, or L0 restricted to T lambda. So in particular, equivariance says that if I have the two maps the projection and the action map, if I take the pullback of a sheaf along those two actions, I have to be given an isomorphism. That's what equivariance means. So in particular, if I consider the action map at a point, so if I restrict this thing here to just like a point, that this gives me a trivialization. Well, I guess it's trivial to the n, whatever, fine. Right, yeah. So we know that at a point it's trivial because it's just a vector space. Right, and this spreads it around. OK, any other questions? OK. OK. OK, then for problem 4, so let's start with part A. So, right, we're supposed to show that the affine Grassmannian is equal to the disjoint union of nk T lambda for lambda in. Right. Or, well, let me write it better. OK. But we know that T of k, well, I'm going to say it's equal, but yeah, to T of O, T of lambda, the union of this. So in other words, This statement here is, well, basically equivalent to saying that, right, like, yeah, let me say that it's equal to nk times tk times go. Right, because we have this TO comes from here, and these T lambda come from here, so we can form a TK. Or, in other words, if we pull back to the group and not just the Grassmannian, we need to check that GK equals BK times GO. But if I quotient by BK, this is saying, well, let me say, yeah, I want to say that GK mod BK equal to, well, the quotient of this. But in order to write the quotient of this, we can also do it by computing the intersection of BK and GO, which is BO. No surprise there. So we need to check that, I mean, yeah, let me say, need to show from there on. So we need to show that BK mod GK is equal to BO mod GO. But G mod B or B mod G is proper. So by the evaluative criteria, so let me write by criterion, the map from B mod G of O surjects onto B of G of K. Well, yeah. In fact, it's an isomorphism, but yeah, whatever. Surjects. Right. And hence, we have an equality everywhere. And yeah, I guess this proves that the union without the disjoint is equal to this. And I would need to be careful to do that there disjoint, but it basically follows from this. But I don't want to check. I don't want to check this. Okay. Okay. So now we want to check that this category of NK chi equivariant D modules has some D module on an NK orbit if and only if this T lambda is dominant. So to do this, we're going to prove this hint that they explain. So we want to prove the lemma X homogeneous H space carries an h chi equivariant D module if and only if chi restricted to the stabilizer of a point is trivial. Let me just say 1 or 0 actually. Okay. Okay, so wait, which one's easier? So let me check that this direction. Right. So let's assume that X has such an equivariant D module M. Well, yeah, some carries a non-trivial, I guess. Non-zero. So let's assume that M is H chi equivariant. Right. So, I mean, it's sort of basically the same idea as we had there. So, what does this H chi equivariant mean? Let me write it out, and then, so it means that if I have the action map and the, well, let me, call this the action map, then I have an isomorphism between the pullback by the action map and, let me say, chi star of L box M, where this L here is e to the x as D module on GA. Okay, so if we restrict this to stabilizer of x cross x, we get that, well, A star now it just becomes the projection to a point. So A star M restricted to stabilizer is just trivial. And this thing here, well, let me say, it's MX tensor trivial, like the stock at the point X. And this thing here is just restricting here to the stock. So it's chi restricted to the stabilizer of X, pullback of L tensor M of X. So we must have that so this implies that K restricted to the stabilizer of X, pullback of L is trivial. And because this is a map to GA, it actually splits. So this implies that, well, if it's surjective, that stabilizer, that chi restricted to stabilizer of X is 0. And now let's prove the other direction, that there exists such a h chi equivariant D module if chi restricted to the stabilizer is 0. And to do this, well, note that x can be identified with h modulo the stabilizer of x. And if chi restricted to the stabilizer is 0, we can define chi bar from h mod stabilizer of x to GA. And we can check that chi bar pullback of this sheave L is h chi equivariant. Any questions about that? And I was supposed to go half an hour, and it's been 40 minutes, so I think I'm done. Any questions? Okay. What? You pull it back to x. I mean, yeah, then, yeah, you can check, yeah, well, whatever. Yeah. I mean, it's basically checking that x, the pullback of the normal chi is h chi equivariant. Yeah, it's the same thing.